That one. Yes. We'll start in about 5 minutes. Yeah. At the top of the hour. I'd like to encourage y'all to sit next to somebody or do some relaxing because I think a lot of times it's helpful if, I can't answer every question. Sometimes the person next to you, if they're interested, let's go to the next slide. Sound check. Is that loud? Is that good? Everything good? How about here if I'm talking? Is this also good? Do I need to lean in? Okay. Yeah. everybody get a chance to get the setup stuff done already? Yeah. All right, we're going to need a little bit more than this. All right, raise your hand if you got the setup done. Okay, awesome. I will take a couple of minutes, or I'll take a few minutes at the start. If anybody had trouble or has questions, we can go through that as well. I'll wait until 8 o'clock, though, to actually start talking officially. Okay, I can hear everybody's alarms going off and notifications. It must mean it's 8 o'clock. So we'll go ahead and get started. Welcome to a practical introduction to NumPy. Thank you all very much for coming. And I want to start with an apology for the frog in my throat. I've been trying very hard to get rid of this for the last few days. It will be our companion during today's tutorial. In any case, I'll do my best to be clear. And I'd like to introduce myself. Again, thank you all for coming. My name is Tim. I am the principal and founder at Diller Digital, and I teach Python and scientific computing for a living. It's a new company I started late last year. And so I really enjoy teaching. I really enjoy helping people learn how to become effective in scientific computing. And so I'm really glad that everybody's here today. I hope that this can be interactive. I hope that you will follow along. I don't have slides today. I'm going to do everything from a Jupyter notebook. And my goal is to type, and I will talk as I type. And I hope that you will be following along, and you can reproduce what what you see on the screen, so I'll try to pace myself so that you can follow along. I'm a firm believer that you learn something by seeing it, and then by doing it, and then eventually it really becomes cemented when you tell somebody else how to do it, right? And so we can get you at least through those first two steps today. My goal also is to give you an introduction into NumPy, the library, and to help you feel confident that you can understand it, that you can understand the why and the how of how it works. There is a lot to NumPy, and there's no way that we can get through everything today. So we'll just get as far as we get, and I will be happy to be driven by your questions. Also, I'd like to point out my associate Alex over here. He's my associate at Diller Digital, and we're happy to answer questions, and he can help me with questions today. So I'm hoping that you all will feel very free to ask questions. So let's just do a little exercise right now. Everybody raise your hand. Let's just make sure it all works. Okay, awesome. And now I would like somebody to raise their hand and ask a question. Give me any question, but I just want to break the ice. Okay. Do I have a favorite Taylor Swift song? Unfortunately, I do not have a favorite Taylor Swift song. Great question, though, but I'm not sure I could even name one. Okay, any other questions? Awesome. NumPy 2.0, what are the big differences? I don't know that I'm prepared to go into big detail on that. Sorry. Okay, another question. The big beautiful mountain that we can see out there is indeed Mount Rainier. It is awesome. It is gorgeous. All right, any other questions before we get started? All right, these are good questions. All right, and so now we've seen that questions are good, and I encourage them. Okay, so before I had everybody raise your hand if you had successfully installed the materials. Can I show a hand? There's no shame here, but if you have, either due to not thinking about it or encountering some difficulty, do you not have the materials downloaded and installed in the environment set up? Okay, we've got 1, 2, 3, 4, 5. Okay, so we have a handful of people. I will start you at my GitHub page, and the address of the GitHub page, I think if you can read it here, it's github.com Diller Digital 2024 SciPy tutorial. That's your starting point. If you are familiar with Git, then you can do a Git clone and just copy this. If you are not familiar with Git, that's fine. There's no shame there. You can click on this handy download zip, and you'll do that, and it will put everything in that repository into a zip file, and you'll download it. I don't have my Wi-Fi connected, but when you download that zip file, what you'll do is you'll move it to some place that you're going to work during today, and you'll expand the zip file. Okay, so everybody do that, and once you're there, okay, so I'm just going through the setup instructions that are right here. So go ahead and do that. It's not a large file. Any questions? Anybody stuck on that? Okay, we're all good. Everybody's happy. Okay, the next step is I'm a very strong proponent in setting up a Python environment. Who's familiar with virtual environments in Python? Okay, a handful of people. Are some people not familiar with virtual environments? Okay. All right, so there are different ways of making virtual environments. I'm a big believer in using virtual environments, and what it is, Probably the best way to explain this is something that we're all familiar with, let's say Microsoft Excel, right? When you download it, you have one working copy of Microsoft Excel, and you have preferences and extensions and everything installed there. And every time you double click on the application, it opens up that one copy. But let's say that you had two different customers and they had two different sets of preferences and extensions, and if you used one on the other, then it would cause big problems. So you might download a second copy of the application. We don't do that with Microsoft Excel because it's not set up that way. But in Python, very often you're working on one project and you have one set of requirements and you have one set of packages that you want to use, and on a different project you have a different set, and sometimes there are incompatibilities between the two, especially because packages are changing. So virtual environments or Python environments is a way of kind of creating a sandbox environment where you have your own Python executable with all of its libraries and packages and dependencies over here, and then you can do another one in a separate place that doesn't disturb the setup for the first one. So there are at least 3 good methods, I think, for using Python environments. The one that I'm going to propose that you do is Python plus pip. I assume if you're at this conference, you've probably got Python installed somewhere. That's the case, right? This being SciPy. Okay. So basically what we're going to do is in your terminal, you're going to come over here and type Python-m. And that -m means that you're going to invoke a library as if it's the main thing. So you're invoking a library as if it's an application. That's what that -m does. And the library that we're invoking is called venv, which unsurprisingly is short for virtual environments. And I just named one called, actually, I wouldn't call it SciPy. I changed that. Let's do it over here. Let's call it NumPy tutorial venv. And so we're just picking a name for it. And so you'll open up a terminal. And if you're on a Mac, you may have to type Python 3, and depending on your situation, in any case, one way or another, you need to invoke your Python. You'll do venv, and then your NumPy tutorial venv. And what that does is it's going to create a new folder with its own copy of the Python executable, and it's going to that's going to be the place that you're going to install any new materials. So now that we have the NumPy tutorial environment created, and I did a bad thing, which was to create this out in my home directory. You'll want to navigate to the folder that you just downloaded. But here you can see it, and I'm just doing this by way of example. So you'll want to navigate into your tutorial folder. But once we get there, then we're going to activate this environment by using the source command if you're on a Mac, or if you're on Windows, you'll just go straight to it, and you'll say NumPy tutorial venv /scripts /activate. In any case, you're looking for an activate script, and what that does is it puts that copy of Python at the head of your system path. And now that's the one that when you say Python, that's the one that's going to get used. And then finally, to install the dependencies for this tutorial, so let me just finish my example here. So here it's bin activate. And then one of the things that's installed is the package installer for Python, also called pip. And then you'll just type pip install. And the 3 that we're going to need for this tutorial are JupyterLab, NumPy, and Matplotlib. So pip install we're telling it that we want these three packages, and those three packages, of course, depend on many others, but those are the three that we're going to make use of. Jupyter Lab is the environment that we're using here. And can I have another show of hands? Who's familiar with Jupyter Lab? Who's worked in it some? And for whom is Jupyter Lab a new concept? Okay, great. So Jupyter Lab is not hard. It's a nice kind of integrated development environment. Can I just have another show of hands if you are just installing this now? Can you let me know when you've gotten through that point and then type the word Jupyter space lab? Okay, got one person, got it. Anybody still working on that? Okay. And you can just let me know if you have a problem with that. Again, the Wi-Fi here is this one, GTC TC public, and that should give you the ability. Actually, I'm going to go ahead and connect because that'll. So that's Jupyter Lab, matplotlib, and NumPy. And so it'll do something on your screen that will look a little bit like this. It's looking it all up online. You can see there's a lot behind the scenes that goes on here. Any questions or struggles so far? You can see there's a lot packed into some of these. Most of this extra stuff that's being downloaded is driven by the Jupyter Lab. That's a list of all of the packages that we just installed. There's a lot there. So now it's working behind the scenes. The good news is that was pretty quick. I think that took, maybe less than 2 minutes to run the whole thing. And so now I've got Jupyter Lab installed. And if I type Jupyter space lab and hit enter, it's going to pop up a screen that'll look like this. And you'll have something that looks like that. Okay, so this is your immediate goal, is to get to a web browser page that looks like this. Who's there so far? All right, some of you are there so far. Who's still working on it? Okay. And does anybody need assistance? I can come around. No, just more time. Okay, no problem. So while you're doing that, I will give a little bit of background about why are we having this. Why do we need a package called NumPy? and I'm going to maybe give you an overview of what we're going to do in the tutorial today. So today in the tutorial, obviously we're doing the bootstrapping stuff, and then I'm going to walk you through kind of a story arc about why do we use NumPy and how do we use it effectively. And I want to start with a discussion of data types, and I want to try to convince you that data types matter, and it is your choice of data types when you're doing computations that's going to have a big impact on particularly on the speed of what you're doing. So why do we even need NumPy? So I'm going to, I'll start by having us try some computations with pure Python, because we can do computations in pure Python, and why don't we always use pure Python for computations? And along the way, I'm going to introduce a tool that we're going to use to to check our performance. And so I'm going to try some pure Python computations, and they'll be small because it's just in the scope of what we can do in a tutorial. But we'll do them in pure Python, and then we'll come back later, and then we'll do them in NumPy, and we'll see how sometimes you get a 10 or 100 or sometimes even 1,000 times speed up in the computations. And then after we kind of set the stage and give you the context for why we want to do this, I'll come back then and I'll introduce the NumPy package and how do we create, what are the data types, how do we use them, how do we create arrays and manipulate them and do the computations. And then toward the end, we're going to be slicing and we're going to be dicing and we're going to do some computations and some exercises that will give you an opportunity to try your hand on this. So also, just a little bit of housekeeping. I think there are going to be snacks out there at 9 o'clock. My typical pace is to talk for about an hour and then to have a break. And so I'm going to try to maybe do 5 or 10 minute break at the top of every hour. And that'll give you a chance to get up and get more coffee and you know, go stretch your legs a little bit. Okay, so is anybody still working on getting to the Jupyter Lab? Okay, do we need help? Oh, Logan's in the field too here. All right. I'll just... Okay, so let's take a quick a quick overview of what we've got here. On the right-hand side, what you're looking at here is a Jupyter Lab interface, and that's fine. So sorry, the Jupyter Lab interface it's similar to other integrated development environments, and so it would be something like VS Code or whatever. I like it because it's very convenient. Everything's kind of all together, and it's Python itself. So what we've got on the left-hand side, on the far left-hand side, if you look, you've got this thin strip over here, and that thin strip has different icons on it. And so the top one being the manila folder looking thing, that will give me my file browser. And the top level of this file browser is the one that I started the Jupyter Lab session from. And then this one right here shows me my working kernels. We can mostly ignore that for now. The one below it right here shows the headings. And as soon as I open up a particular IPython notebook, this is kind of like the outline, the overview of a notebook. And then this is plugins. We're not going to worry about that so much. So for right now, I want you to have the manila folder open, and you'll look to the right of it. You'll see a big blue button with a white cross on it or a white plus. And that plus is, what that does is it opens up a new tab over here in the main work area. We don't need that right now because what I've got for you here, if you started Jupyter Lab from inside the zip that you expanded or extracted, then you should have something called the SciPy 2024 NumPy tutorial. If you double click on it, you'll end up with the notebook over here on the right. And then you can click on the folder again and give yourself some more screen space. So if you can, go ahead and navigate to this place, and I'd like everybody to be with me on this at the same place on the at the top. It should say Practical Introduction to NumPy, and then you have a Jupyter Notebook. If you've got some other development environment like VS Code and you can open up this NumPy tutorial notebook that way, that's fine too. But this is an easy way for us to all be on the same page. Anybody need help getting to here? We all good? Everybody's with me? Okay. So all of this bootstrap material is here, and we can move past it. So I'm going to give a quick orientation to Jupyter Notebooks. I've already talked a little bit about the Jupyter Lab environment. One of the things I'll point out to you is that one of the things that you can get when you do the launcher, so remember there's this blue button. You can also get that depending on your version of Jupyter Lab. You'll have a little plus right here that you can use to get a launcher. So you can start a new notebook if you like. The other thing that's useful is to open up a terminal session. And this is a terminal session that's running in your browser, so it's kind of a interesting, I don't know, sort of a nested thing right there. But for the purposes of this tutorial, we're just going to, we'll just stay in the notebook like this. So if you look on the notebook, there's a couple of different things. A notebook is made up of cells. And as I'm going through this here, it doesn't look very much like computer code yet. But what you can see is I've got different cells. And as I'm moving between these cells, you can see there's a blue bar on the left-hand side. And that shows kind of the idea of which cell is the current one or the active one. And I've got two different kinds of cells in this notebook. One is called a code cell that actually contains Python code. Logan, thank you so much for your help. The Python code in a code cell can be executed, and you can use it like regular Python code that would be in a script or in an IPython session. Then there is a second kind that's called a markdown cell, and that's what I'm using here to show the formatted text and everything. And so if you're familiar with Markdown, if you've ever heard of that, it's a little bit like HTML, but it's less complex, and it's designed to be readable. This is in a particular kind of Markdown that's called GitHub flavored Markdown. And I've put a Y and an M there to show you, and I'll say what those are in just a second. So there's two kinds of cells, and then the Jupyter Notebook itself has two modes. And there's what's called a command mode, and there's what's called an edit mode. And right now, I'm in what's called the command mode. And I know that I'm in a command mode because, well, because there's no blinking cursor. I've just switched into the edit mode, which is where I can type and make changes to the contents. And when I execute that markdown cell, then you can see it renders it into nice HTML, and we can take a look at it. And so enter changes from command mode to edit mode, and escape moves from edit mode into command mode. Okay, so if you can see a blinking cursor, it means that you're in the edit mode, and it will look like the cell itself has some depth, and that means that you're in the editing mode. And otherwise, if you're in the if it has sort of a more flat appearance like this, then that means that you're in the command mode. And things that you type will affect the cells; they won't add text. So I've got a screen here. Let's see, maybe I can squeeze this all on like this right here. So you can see there's the command mode and the edit mode. And when you're in the command mode, you can type things like A and B. So A will insert a new cell above the current cell. B will insert it below. You can type D twice and get delete cell. The arrow keys will move the selection up and down. So I'm moving up and down with my arrow keys right now. Y, if I type Y, it will change it to a code cell. M will change it to a markdown cell. And unfortunately, I'm sorry, the keyboard shortcuts, they don't work. That's a typo on the slide here. In edit mode, you've got other things. So for example, I'm going to type, if I look over here right now, I'm in the command mode, so I'll type B, and I've got a new cell. By default, a new cell is created. When a new cell is created, it's a code cell. And so you can see this is the new cell, and I know it's the selected cell because it's got blue on the left-hand side, and I know it's a code cell because it's got a pair of square brackets and a colon. And so I will press enter to get into edit mode. And I can type some Python code. If I press enter now, what happens is I get a new line. It doesn't execute the code. And so I can put in a whole lot of lines of code together like so. And I want to point out just a couple of other things. 2 plus 2. Let's so I've got code like this, and let's say that I want to make some changes. I'll just point out a couple of things quickly. If I wanted to suddenly turn these codes into a code block, then I can select them and press the tab key, and it will automatically indent. So I have a lot of the regular code editor features available here, including some niceties like I can hold down the command or the control key and get multiple cursors. That all works in Jupyter Labs, so I can make changes like that. Those are all features of the code editing that happens inside a Jupyter Lab session. So to execute the cell, I've got 3 options. The most usual one is to hold down the shift key and then press enter. And that will execute the code that's in that cell, and then move on to and then move the selection to the next. Then the following cell becomes current. Another thing that I can do is I can hold down the control key and press enter. And now it executes it and doesn't advance the current cell. So it stays on the current cell. And then finally, I can hold down my Option or my Alt key. And this is one that I'll be doing a lot because I have some cells in place already and I want to insert. So if I hold down Option and press Enter, it will execute the current cell and insert a new one below. So those are 3 kind of shortcuts that you can use for executing code. Another thing to note about, and today's tutorial is not about Jupyter Lab, but it's helpful just to have these things. You'll notice that above, where it says 3, every time that I've executed it, the output number has incremented. And so one of the things to pay attention to in a Jupyter Lab session is that it's possible to execute cells out of order, and that can lead to some funny statefulness. So just be aware of that and kind of keep that in mind as we're going through as we're going through the tutorial today. And in a pinch, if you find yourself in a weird state and you're getting errors that don't make sense, one of the things that can be helpful is to come up to the Run menu and you can restart the kernel and run all of the cells. And what that does is it will sort of wipe out the Python memory, and then it will run everything again from the top. And go through. You probably don't actually want to run all of the cells every time. You can just press the square right here that will interrupt the kernel. It will stop it. It's this one right here. So if you've got something that's taking a long time and you want to interrupt it, you can press the square, which is kind of like the stop button. And this circular arrow will restart the kernel and give you a fresh start, and then you can start executing from the top again on the way down. So that's a very, very brief introduction to Jupyter Notebooks. I think it will help. Maybe that's enough if you've not seen this before. That'll be enough to kind of help you get started. Any questions about Jupyter Notebooks? Does that make sense? Yes. Okay, you're trying to go back to command mode, and it's looking like this, and you're pressing escape, and it's not working? Okay. Well, so one of the things that can happen is maybe you've got something
like here, for example.
Oh, okay. Okay, so he's got a great point here. So there's one other thing that I should mention here. If you'll notice, if you look, let's take, for example, my bootstrap cell right here. If I turn this into edit mode, you'll see that this is what the markdown looks like. And I'm using hash marks for titles. I've got special syntax for making links. I've got 2 pairs of asterisks either side to make it into bold. And if I just press escape, what happens is I'm back in command mode, but what happened was it didn't execute it. So I didn't execute the markdown to render it. So what I would have to do is press command return, and now by executing a markdown cell, it renders it into the HTML. I chose command enter because I didn't want the focus to move to the next one down, but shift enter, any of the ways of executing it. And while we're talking about that, one more thing, if I was to make a change over here, I had thought it was going to work there. Let's see. Maybe it's here. Okay, depending on the version of Jupyter Lab that you have, some versions of Jupyter Lab, and I get lost because I kind of jump around to different ones. Sometimes this sidebar on the left will turn orange if you've changed the code. And what that means is that the output below no longer matches the, no longer accurately reflects the input, the code that you have there. So I don't know if you may experience that. It varies somewhat based on your platform and your version. I'll point out one more thing maybe. If you look on, and this is more related to just kind of the syntax of IPython and how that works. But if you look up here, I've got print hello world, and what print does is it displays to the standard out. And so you see I've got some text output right here, and there's nothing to the left of it. If I evaluate an expression and execute it, you'll notice that what happens here is now I have an output cell, and this output cell, there's a 4 here, an orange 4 to match the blue 4, and that means that something was returned, and that's something that I can work with. And that's just a distinction that I like to make about the difference between a print statement which displays something to output versus evaluating an expression which returns an object. That'll come up a little bit. But that's probably enough of the bootstrapping. Any other questions? Yes. Yeah. Yes. Okay. Great question. So what you can do, you've got multiple options. You know that this is a code cell a couple of different ways. One is by the pair of square brackets. The other is up here at the top where it says code. So you can come up here and manually change it back to Markdown, or you can also you can type the letter M, and it will have the same effect. And then you'll hit Command Return, and it will render. Okay, are we happy? Everybody's happy? All right, awesome. So let's talk about why NumPy. And I like this. This is what we sometimes call our ziggurat diagram. And I like to use this to show kind of what is the relationship of all of the stacks. Like we're building something, we're building applications, we're doing scientific computing. And so we're all here at the SciPy conference because we like to use Python. And so Python, the version of Python that's most often used is called CPython, and it's CPython because it's written in the C programming language. And so Python has a lot of, inheritance. It's informed very much by the nature and the structure of the C programming language. And this is going to turn out to be really important for us in a little bit. But we're going to we'll take a look at that. So at the very foundation is the C programming language, and that is what was used to write the executables that the Python runtime executables. And there is an extension to Python. So above and building on it is the NumPy library, and this is what we're going to be talking about today. And NumPy inherits both from Python. So it's a Python interface, but it also has some relationship to Fortran. And I'll talk a little bit about the difference between C and Fortran. It's going to matter that some things come from Fortran and some things come from C. And SciPy is not only a fantastic conference, it's also a library. I think we're all familiar with that. And SciPy is the Python interfaces to many scientific algorithms, some of which are implemented in C, but most of which come out of Fortran. And so NumPy provides a data type that is fast and efficient for computations in scientific algorithms. NumPy also is a major dependency for the matplotlib library. Matplotlib is the primary plotting library. I imagine a lot of you are familiar with that already. And so as we'll see, NumPy is kind of a general purpose it's a general purpose library that provides a lot in terms of array computations, fast computations, and so forth. And because it's very general purpose, sometimes it can become a little bit unwieldy in certain cases. So there's another library called Pandas, and you've probably heard of Pandas if you've been around this community very long. And Pandas trades some of the generality of NumPy to make certain specific use cases very, very simple. And by the end of the tutorial, you'll get a flavor for what some of those use cases would be. So NumPy sort of sits at the heart of what we call this whole ecosystem of of libraries in scientific computing. And there's a whole bunch of others that all depend on NumPy. There would be things like Xarray, which provides array kind of data with axis labeling, and you can put like geospatial location information in it. There's one called Awkward Array, which deals with arrays that are not regularly spaced. There's Plotly, which brings a lot of this into web-based visualization. Seaborn is visualization that includes a lot of statistical utilities, etc., etc., etc. So there's computer vision, there's statistics, there's machine learning. And it all makes use of NumPy. And why is it so important? Why is NumPy so important? Well, it turns out that data types matter, right? So I'm going to spend some time talking to you about data types and why they matter. And we're going to start by talking about types in Python, right? And so I'm assuming that everybody here is familiar with Python, that you have some familiarity with it. And if we were to imagine that we wanted to do some kind of computations in Python, we might look for what we call the container data types. The container data types would be things like lists, tuples, sets, where we can put more than one value collected into a single object. And so if you look, a list is you create a list with square brackets and commas, and it's dynamically typed, meaning you can put anything that you want to into a list. You can have a string followed by a number, by a float, by a function. You can put lots of different kinds of things into it. A list is ordered. It can be changed, so it's mutable in size. You can make it longer and shorter and so forth. And one of the important things is, like, lookup time, for example, is order n. So depending on how large your list is, it takes successively longer to look it up. A tuple is a lot like it, except now we're using parentheses instead of square brackets. And this one is immutable, so it's fixed in size, and it has that same order n lookup time. And set is another one. This is also dynamically typed. It's not ordered, it's mutable, but the reason I bring it up is because of its order 1 lookup time. And the point that I'm making here is not particularly about computations, but it is about the fact that the data type matters. And so I want to introduce you to a tool called TimeIt. TimeIt is what we call a magic command. Magic commands are a class of commands that belong to the IPython library. And IPython is also kind of a predecessor or an ancestor of Jupyter. And so Jupyter and IPython provide these things called magic commands. And the magic commands are indicated by a percent sign. I like to think about it as, if you kind of imagine tracing out a big percent sign, it's a little bit like you're doing magic hand waving to make things work. So percent TimeIt will work on a particular expression, and you can run that expression multiple times and see how long did it take to execute that expression. You can do 2% signs and time it, and that will work on a whole block of code. And we're going to use both of these to just kind of show you how to kind of make my point about data types matter. So in this block of code, I'm just creating a list, a tuple, and a set. And each one of those is made out of a range with 10,000 elements. Okay? And I'm going to use the timeIt command to see how long does it take to see whether the number 9,999 is in the list, in the tuple, and in the set. So I've already written this in there for you, and if you just execute this cell, you'll get a little star there, and that star indicates that it's thinking. And what it's doing is it's running these maybe 100,000 times, and it's performing statistics on it, and it's profiling it. And it showed us that the lookup time in a list with 10,000 elements was 102 microseconds. And in a tuple, the lookup time was 95 microseconds. And in the set, it was about 35. Right, so the set is about 3 times faster. Or, yeah, I mean, there's a factor of 3 difference in the speed of lookup between a set and a list. Yes? Yeah, it's a good question. So he's asking why did this one look up over 10,000 loops and this one about 10 million? Oh, I'm sorry. It's not microseconds. This is nanoseconds. Sorry, there's a whole order of magnitude difference here. So there's 3 plus 3 orders of magnitude. So this is a 3,000 time difference between the two. So a set is that much faster in looking up. And what timeIt does is it tries to figure out how many times do I need to run this, or it wants to maximize the number of time that it runs it, but it's going to pick the number of loops that takes about the same amount of time. So if I have something that executes really fast, then I can do it 10 million times and get better statistics. And if it takes a little bit longer, then I'll only run 10,000 loops. So, yeah, sorry, I should have known better, but what I was trying to point out here was the data type really does make a big difference. And a lot of knowing how to program efficiently in Python is knowing what's the right data type do I use. And so if I'm looking up something, you may want to think about, okay, let's choose the right data type and make sure that we're doing the right data type, because in this case here, you can see we have about a 3,000 or 2,500 times speed up. Incidentally, I want to point out, yeah, let's see. Incidentally, let's do this. I'll do another timeIt here. And what I'm doing here is I'm just showing you that it takes a non-zero amount of time to look up a data type. Go ahead, question. So the underscore, I chose to put an underscore in there. This underscore is just a little piece of syntax that it's not interpreted at all. It just shows, it's the equivalent, like what I would like to do, because I'm an American and I'm used to seeing numbers displayed like that, 9,000. So this is kind of a syntactic equivalent of the comma that I use for separating orders of magnitude. So I can just show you that timeIt on type of L500 is, even though it's fast, it's a non-zero amount of time to look up the data type of something. And one of the things that we like to talk about in teaching Python is that when you do computations, you know, Python is dynamically typed, and so I can add integers and floats, and I can do all different kinds of things, and Python will figure it out as it goes. I don't have to work everything out in advance. But the point that I'm making here is that it takes time to look it up, and it takes time to find it in memory, and it takes time to do all of those things. So So those are all, like, you can kind of think of them as attacks on the computation. So let's think about some computations that we might do in Python, and we're going to come back and do these in NumPy. But I want to do these in Python just to kind of show you what's going on. And I've got, well, this looks pretty simple. It's just going to be y equals x plus 1. But what I'm going to do is I'm going to create x as a range of values, and then I'm going to add 1 to each value of it. And let's just kind of show what the pattern would look like if we're doing that in Python, and we'll use time.it to kind of get a sense of how long that takes. So typically speaking, if I would say a range of 1,000, something like this. And then, I don't know, I've got two different patterns that I could do this. Perhaps the one that you might be most inclined instinctively to do would be to say for value in x, y dot append x plus 1. What did I type wrong? Can only concatenate, oh, sorry, it should be value plus 1. Okay, and so this is what a typical computation would look like if I was just doing it in pure Python. And because this was a very small example, we do it quickly and it's fast, and we don't worry too much about it. But let's just take a little reference here, and I'll use the block time.it right here. And so I've got the two percent signs, and I run time.it, and it's going to run the whole block of code multiple times. And you'll see that I'm at about 62 microseconds to do this simple computation of just incrementing a single value. Okay, so this is going to bring us to our first little exercise. It's a trivial exercise, a mostly trivial exercise. And so we'll take until the top of the hour, just kind of work on this on your own. But using the example that I just did right here, with this time.it x equals a list, I've given you the x starting point right here, okay? And I just want you to do a computation and time the computation of y equal to the sign of x. If x is an array, and this is an array in Python, and I realize I'm taking a lot of time to talk about the wrong way to do things, but I'm trying to give a baseline for what's going on here, and we'll see how this gets faster. So let's take a few minutes. You'll execute this cell right here, and I want you to reproduce the pattern that you see up there in cell 9 and put it down here. And all that you're doing is you're going to compute the sign of x. If you know how to do this in a list comprehension, that's just fine. And when you're finished, you can feel free to go up and grab coffee. Let's say at about 10 after 9, I'll just kind of walk through the solution, and I'll be here walking around. So work on this for 5 minutes, and then we'll take a 5 minute. Yeah, let's start up at about 5 after. Okay, so one quick note is that when you do time it, when you run the time it magic, this has to be the first line of a cell. And yeah, like even a comment line before that will cause it to be invalid. All right, I'm gonna do my best to get started back on time. Um, okay, so I had set an exercise to compute the sine of x using kind of the same pattern that we had before, and I gave you x already. So if we execute this cell, you'll notice also that there's something up here that I've imported pi and sine from the math library. And I'm doing this on 101 points. So I'll create an empty list, and I'll say for value in x, y dot append sine of x. Sine of value, thank you. And boom, that's done. And if you like, you can also you could do this in a list comprehension. You could say sine val for val in x. It's another way of doing it. Like so. That's a more compact way. Sometimes that can give you a little boost in computation. And so I have these in the solution that you can expand. One thing I want to point out though, and I'll do it by way of introduction right now. So if you expand the solution right here, you'll see that I've imported the matplotlib library. Who's used matplotlib before? Okay, is it brand new to anybody? So I probably don't need to spend time on matplotlib. Okay, and so I just thought for the purposes of completeness here, that I would give a brief introduction to the plotting program, because that lets us take a look here. Okay, so now just for later comparisons, I'm going to do time-its on both the for loop and the list comprehension method. And you can see that the for loop took about 6 microseconds and the list comprehension took about 5.5. I'd call that roughly equal. The list comprehension gives you a very minor gain. Now I want to also do a baseline, and rather than take independent time on this exercise, because I want to come back and show you this one later with NumPy in a much more efficient kind of way, let's just live code it together. But if we wanted to compute the derivative of the sine of x, like the numerical derivative, and so we would have dy of dx, where y is the sine of x. We're going to approximate that using the deltas between the elements of y and the elements of x. And so at any given point, we're going to have delta y over delta x at I is going to be y of I plus 1 minus y of I over x of I plus 1 minus x for all of the i's up to the length minus 1, right? This whole operation requires us to reduce the dimensionality by 1 because we have the plus 1 there. So let's just let's live code this one together. I'm going to come back and revisit this one later because I have a good point to make with it in NumPy. But we're going to we'll see this one and we'll get our baseline right now. So I'm going to do for I in the range to the length of x minus 1 And now I'll do my dy equal to y of I plus 1 minus y of I. So this is all just normal indexing, and I'll do my dx in the same way. I plus 1 minus x of I. And if I did this right, I'll do plt.plot, and I'll get x and y, and then I'll do plt.plot of x up to, but not including the last one. Oh, sorry, I skipped a line on here. Now I need to do dy dx dot append dy divided by dx. That's actually that's the most important computation right there. Okay, and so now I'm going to plot them. What did I do wrong? Dy dx. Okay. And if I did this right, then I get a sine wave and a cosine wave. And I hope that this approach here feels instinctive to you. Like this is kind of, it makes sense, it's intuitive. And I'm going to show you another way and try to help you get an intuition, a better intuition. But does this make sense? I know based on experience that sometimes for people in science and engineering, it's been a long time since you learned calculus. Some of you use it on a day-by-day basis, and some of you haven't touched it in decades or more. And so I just wanted this to be kind of a gentle reintroduction. So let's do a time it here and see how long, and just kind of get a baseline for how long does it take to do a derivative computation. I think we have 101 elements in there. Okay, so 12.4 microseconds. And you can see I've got all of the stuff in here. It's the same thing, that solution. Okay, so if you look, what's going on here is I've got a markdown cell that is a title, and the way that it's a title is I've got those hash marks. And so this is a level 4 sub title. And this version of Jupyter Lab on any title will give you the opportunity, like if I'm just clicking this little button right here, it'll collapse everything below that level. Okay, so I think I've started by showing you just sort of the pure Python. I've made a couple of important points here. One is that data types matter, and two, I've kind of showed you a baseline for how computations might work in pure Python. It is certainly possible. And why then do we want to do the NumPy array? And I'm about to make the point to you that the kind of computations that we just showed right now are not very efficient in Python, because there's a lot of data type checking that has to happen, and a lot of dereferencing and memory shuffling and everything. And Python is designed to be very easy to understand and write, so that you don't have to worry about the types and everything. But that comes at a cost. It's like a tax on the computation. So what I'm going to do now is class meet the NumPy array. NumPy array, this is the class. And I'd like y'all to get acquainted with each other. And I'm going to give you a comparison between the Python list, which is dynamically typed, it's ordered, it's mutable values and mutable length, and the NumPy array. And the NumPy array comes from the NumPy package, and the data type is ND array, and I'll talk about what ND means in just a second. And this is statically typed. In other words, once you fix the type, it's fixed, and you can't change it. It's also ordered. The values are mutable, but the length of the array, the amount of data in the array is fixed. It's also a fixed thing. And so by having this static typing and the immutable length, what we've done is we have now we've changed the trade-off. We're going to give up some of the flexibility and generality of the Python data type, which is the list, and we're going to use we're going to restrict it somewhat, and we're going to get a whole lot of performance out of this new data type. So the way that we get NumPy typically is to import it and to do an aliased import. And so this is a very common way to import NumPy, is to import NumPy as NP. It's a very common renaming of NumPy on import. And the reason that we do that is then it becomes very obvious where your values are coming from and so forth, where your functions, where your data types and everything. So just this little np.array just means that, okay, we got it from NumPy and now we know. And that's important when you have things like np.hist, which would be a histogram, and that might interfere with the IPython hist, which is the history. And so I'm a big proponent of always using that that shortened prefix to get things. So we'll import NumPy as NP, and then we'll create an array object right here. And I just made an array out of a range of 10. There's a better way to do it, but I'm trying to introduce things one at a time. Excuse me. And when you look at how this is displayed, you'll see that there's it comes with the leading name array, and then there's a pair of parentheses and some square brackets. And we'll see eventually that you can end up with multiple sets of square brackets, but this is a simple array with 10 elements. And I'll point out a few things to you about it. The first thing is, let's just take a look at the type, right? It's the NumPy ND array. Like I've already said, that's where it comes from. Yeah, and so indexing and setting work the same as as for a Python list. So if you're familiar with Python lists, all of the indexing operations, including different kinds of slicing, works. So you can pull out a particular value. And now notice all of a sudden we've got something new in the world. And it says that this is an int64. And int64, anybody here kind of know what that means when it says int64? Can you? 64-bit integer. It uses 8 bytes to create, and so we could figure out if we wanted what's the maximum value, whatever. Anyway, it tells us that it's an integer of a particular size, and now that is a feature of the NumPy array. So watch what happens. If this were a Python list, and I did something like this, then I would see in position 4, I would now see a 9.786. But instead, what I see is that there's been a type coercion. It has coerced the data type. So I'm not free to change the data types of the elements of an array willy-nilly anymore. It's fixed. And so when I made this assignment, there was a type coercion that happened, and it conformed it into that same type. And I can do all of the same kinds of things that I can do if I want the first two elements, if I want the last two elements. I'm hoping that this notation here is familiar from slicing notation in Python. It's the same way that slicing works in Python for lists. I'll come back and talk about that more in a minute. Okay, so I showed you that I can create an array just by giving it some values in there. But there's a large collection of convenience functions, and probably the two most important ones for the purposes of a tutorial or something like this, or defining some kind of computational domain, would be the arange function and the linspace function. Arange works in much the same way that the range function works in pure Python. Although range doesn't actually produce a list, it produces a generator, an iterator of some kind. But in NumPy, the arange function, it actually creates the array. So it doesn't just create an iterator function. And it creates an array of values in the range, starting at start, stopping at stop, with a specific step value. Probably the most important difference is that you can use non-integers for start, stop, and step. And also arange, well, like I said, arange actually returns the NumPy array, unlike range, which returns an iterator. So arange is useful, and it has the same convention of starting at the start and going up to but not including the endpoint. So you may be familiar with that kind of. So if we do this in pure Python, so if we make a list out of a range starting from 2 to 10 in steps of 2, you'll see that we get 2, 4, 6, 8, and it doesn't include the endpoint, right? Maybe you've been through that whole gymnastics of getting your head around that, but that whole endpoint non-inclusive still works here. So the np.arange to 10.2 has the same behavior. The trick is, though, that now we allow it to do things like so we're going to go from 0 to Logan, what's the magic combination that gives us our floating point problem? Is it 2.7 in steps of 0.3? No, might be 2.7. Okay, so in that case, it worked like I expected it to do. And this is the kicker right here. Sometimes, because of the way that binary floating point numbers are, floating point numbers are displayed in binary, and particularly around the use of 0.3, you can sometimes end up with weird behaviors where this looks like it's endpoint inclusive. So it went 0.3 blah 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 right up and included the 2.7 at the end. And this is one of those weird differences where you have, was it 2.3 plus, is it 1.4? Is that Is that the one? Yeah. So for example, if you look at this addition right here, you can end up with odd combinations, right? Because this 0.3 isn't exactly represented in the IEEE standard for floating points. You end up with a number here, 3.7, that is off by like 3 in the 16th decimal place. And this is every computer programming language that uses binary floating point number is subject to this kind of thing. And this can kind of jump up and bite you in the world of NumPy with a range, because what it's looking for is it's comparing this 2.7 with this 2.7, and it turns out this 2.7 may be off by something tiny in the 16th decimal place. And because of that, I caution you, when you're using the A range, just be aware that that kind of thing can happen, because now we're in the world of floating point numbers, and comparisons with floating point numbers are subject to this phenomenon. And because of that, I tend to prefer to use because I'm lazy and I don't like to think through that math all the time. Plus, I don't always know exactly how many elements I'm going to end up with. I will often prefer to use the linspace command, which allows me to set the endpoints and the number of values, and it just does all the math to figure out what's the step size. And I specify the endpoints and the number of elements, and that's how I end up with something like this linspace, and I can go from minus numpy.py to numpy.py in, say, 11 steps. I have to spell it correctly. And so it works that way pretty easily. I'll introduce another couple of these. There is numpy.ones, where I can tell it if I want 10 ones, then it will give me an array of 10 ones. I can do np.zeros, which is pretty handy sometimes. There's also such a thing as np.empty. And what NumPy is doing here is it's allocating the space, and it doesn't bother to fill it with anything. So this just happened to find a place in memory that was full of zeros. I'm not sure why there's a reason for that. In various times that I've used this, sometimes np.empty gives me just really random results. But this one does not take the time, for example. It doesn't spend any computational resource on filling the values. And the reason that you might do that is you might say E equals np.empty with 10 elements, and then you might come in and say E.fill with 4.567, right? So if I wanted to fill in that array, and the reason that I would want to do this is let's pull out our old friend TimeIt. And let's say A equals np.ones times 4.567. And then we'll compare that with a TimeIt here of A equals np.empty. Well, I'll copy from up above. So it's the same result, right? and I went from 2 microseconds to just under 400 nanoseconds. So it's about twice as fast at allocating, like of populating an array. And you know, in the space of a tutorial, we don't notice the difference between 400 nanoseconds and 2 microseconds, but when you expand that over a very large kind of computation, that's why you might want to start with something empty and then use the NumPy fill to fill it up. All right, so I want you to try this. Remember that previously in our exercise 1, we had an array that started at one end with negative pi, and at the other end had pi, and it has 101 elements. So I want you to create a NumPy array, and let's take 5 minutes. Maybe you can scroll back through your list. I would encourage you also, while you're doing this, remember the two things that we learned about np.arange, np.linspace, ones, fill, and so forth. Always keep in mind that you can do something like arange, and then you can type a question mark, and that question mark will give you access to the inline documentation. So I'm going to press Control Enter here. And now I'm going to right click on the contents below and select Enable Scrolling for Outputs. And now I can scroll through the docstring on arange. So I encourage you to spend a little bit of time to look at our array creation functions that we just learned, and then recreate the list from exercise 1 as a NumPy array from -pi to +pi and 101 elements. we'll go one more minute. Okay, so let's walk through a couple different ways to do this. The easy, I don't have to think too much about it. I'm lazy, and this is my normal way of doing it. Would just be to type in from minus numpy.pi to positive numpy.pi in 101 steps, and boom, that's got it. That's basically that's the same thing. We did it. If I wanted to apply a little bit more, I don't know, I wanted the exercise, the mental exercise, I would take the step is equal to times what numpy.pi divided by, let's see, I have 101 elements, and so that's 100 steps, and so I have to do 101 minus 1, so 100 like this. And let's do x2 is equal to np dot a range from minus np dot pi to np dot pi plus the step and by step. And I think that's right, but this looks ugly to me. And in addition to doing all that complex math, the reason that I don't like to do this, let's take a look here. Okay, so if I look at my in my linspace where I have explicitly tagged the ends as being minus pi and pi, if I look at the last element of x made with linspace and I subtract pi from it, and then let's do the same thing for my second one made with a range. And in one case I get 0, and in the other case I get this 15th decimal place difference. So again, maybe I've made my point. I might be belaboring it a little bit more, but just understand that when you're dealing with floating points, you sometimes have sticky things happening at the edges. Any questions about the array creation functions? We've done ones, zeros, a range, linspace, empty, and fill. Does that all make sense? Yeah, is there, so if I took the np.pi minus pi from math, Logan, do you know any reason why those are, like, is there any kind of typing difference? Oh. Okay. Yeah. I'm not prepared to go into all the detail of what he explained. I will get into d-types in some in some depth, but I would say that the numpy.pi, like mathematically, I think in terms of their value, they're exactly the same. Like there's not any difference, and maybe just functionally in how they behave, there might be a little bit of something. So let's go ahead and talk about something called a d-type. I've talked about this a little bit by saying that NumPy arrays are statically typed. And I said that there is a data type associated with the array, and every element of the array has a data type. And that data type is known functionally as the D type. And so if we take our, let's see, I think we said A equals NP. I think we said this was an A range. Right, and I look at the D type. What I get by default is called the D type, and that D type, what I get by default is a D type that is inherited from or inferred from the value that was used to create it. So if I give A range an integer value, it will propagate into the default data type of integers in this version of Python on this machine, which is the 8-byte integer or the 64-bit integer. And if I was to do something, well, and as I showed you before, if I try to put in a different value here, so if I tried to set element 2 to 5.5, it gets coerced into the D type. So I can override the D type and give it something different. And in the case of my array B, I can tell it I want a range 10, and now the D type is going to be float. And notice here I'm using, this is just the Python data type, right? That's a Python float, and so it's going to infer the D type from the system that I'm using. And you can see in output 47 I've got an int 64, and on output 49 I've got a float 64, which is a pretty good indication that my operating system is a 64-bit operating system. And that int 64 and this float 64 both inherit from the default data types of the C programming language on this that was used to compile Python for this machine. I'm kind of curious, does anybody did any of you get a different value? Is anybody coming up with like an int 32? Yeah. And what machine is yours? It's a Windows. Yeah. Yeah, and you've also got a Windows. Yeah, so I would expect some of us to have 32 and most of us probably to have 64. And the point is that inherits from whatever is the native type. And you'll notice also here that this float 64, that's the same size, the data type size, as the double precision floating point integer in the C language. So let's see. I want to have a short digression. Oh, okay. And you'll notice if I do the same trick now that I have a floating point number, I can assign a floating point here in my array, and that assignment happens with no trouble. Okay, I want to have a short digression about print options. Some of you may have discovered already that displaying NumPy arrays in Jupyter notebooks can be a little bit awkward at times. It's about to get more awkward if we don't pay a little bit of attention to the print options. So NumPy gives us something called the print options, and if I call numpy.getPrintOptions, what it's going to do is return a dictionary of different options that we have. And there are things like edge items and threshold and precision and so forth, things like the line width. And what I want to do is I want to change the print options to make subsequent things appear a little bit more a little nicer. So if you'll call np.set print options, and then you can override any of those values. And for my case, I'm setting precision equal to 3. I don't need to see 8 digits of precision. I'm just going to set it to 3. And I'm going to set my line width to 100. And I may need to come back and change that because the resolution changed when I plugged into the projector. But this will give me, what this line width does is it shows how far around it goes before NumPy will wrap onto a new line. And so I'll just execute that right here. We'll set that, and we'll just kind of keep in mind I may need to come back up to line 52 and redo that. Okay, so let's, I've talked about the array, a little bit of how it works and how you create them and how you manipulate them. Let's talk about the computations. In pure Python, you saw that we had to do a for loop, and we had to go over every item in the for loop. We had to take each item and do the computation on it independently. One of the fantastic things about NumPy is that the computations are all vectorized, meaning that no for loops are needed. And in fact, if you're using a for loop, it's a pretty good sign that you're not using NumPy correctly. So generally speaking, for the most part, we're not going to use for loops to cycle through the values of a NumPy array. If you do, it's an indication that something is not factored correctly in your code. So you'll recall that I have A up here, and it's an array from 0 to 9. If I come down here and execute A plus 1, you can see that all I had to do was type A plus 1. I didn't have to do a for loop and iterate over all of the values. I just did a very simple increment of every value. And so this happens in a vectorized way where 1 gets added to every value of the array. So let's try to time it on A plus 1. And while that's working, I'm going to come back up and look at our benchmark at the top. And up here, we had a range of 1,000, so I'll probably need to go back and change it. So to increment every value in a range of 1,000 took about 62 microseconds. Let's come down here. Okay. All right, I'm going to type, so I'm in command mode. I'm typing A to insert a cell above. A equals numpy.arange 1,000, and this will make it comparable, directly comparable with our previous one. And we'll time the incrementing A plus 1. Okay, so we went from 60 microseconds down to 1 microsecond. And then here's the for loop version again, just to show it. Okay, and in this case, using the for loop like this, I've got, what, a full 3 orders of magnitude speed up going from the for loop. So recall that in the earlier example, I had a list, and I was iterating through the list and incrementing the values of the list, and that took about 60 microseconds. The vectorized NumPy version brought that down to 1, so I went from 60 microseconds to 1. But if I put my array into a for loop and try to do this in the for loop, Oh, wait. I'm doing something wrong here. This should have been x plus 1. That's not a fair comparison, what I just did here. That's okay. So now I'm doing my NumPy comparison. Okay. Anyway, my point still stands that putting a NumPy array into a for loop is a bad idea. We don't want to iterate through the values of a for loop. We just want to take the vectorized style notation. Have I lost anybody when I'm talking about vectorized notation? Does that make sense? If you're happy and you know it, give me a thumbs up. If you want more explanation, okay. Okay, so what's happening here? Have you guys come from, say, a MATLAB background? Have you used MATLAB? No? Okay. When I talk about a vectorized operation, what I mean here is that A is a vector and it's got 10 values in it, and and when I say A plus 1, I mean that 1 gets applied all at one time. Well, not all at one time, but it gets applied to the elements individually. And I don't have to explicitly, so just a vectorized operation means that that I'm treating A as the whole vector, and I'm treating it as the whole thing at a time. And I don't have to go through and work on the elements individually. That's all that I mean when I talk about a vectorized operation. It means that I don't have to pick it apart and deal with everything individually. And this is really the power of NumPy, is that you have these vectorized operations. And what's happening is that under the hood, Python actually, so there are these, well, okay, so I'll explain it right down here. So in addition to the data type itself, NumPy comes with lots of functions that are designed to take advantage of the data structure of the NumPy array. And those are called universal functions, or sometimes also called ufuncs. And so hiding behind this plus sign, when you have a NumPy array on one end of the plus sign, what's happening is a very fast NumPy ufunc is going into action to perform that operation. And what it's doing under the covers is it's optimizing the memory shuffling and moving a set location in memory. I'll show that a little bit later. I have a diagram to kind of explain it. But the fact that you can use that ufunc means that you have to check the data type precisely one time, right? Remember we said that the NumPy array, all of the elements of the array have the same data type? Well, that's a guarantee. It's a restriction, but it's also a guarantee. And that guarantee is I can move a specific number of steps in memory, and that will, and so I can set up a very fast operation at the machine level. So there are some examples of things like the NumPy comes with a sine function. And if I call the sine function on my A, and this is where print options, notice that my A range here is set to 1000, and I should have set it to 1001, because when we did our print options, you notice the threshold right there where it says 1000. That means any array that has more than 1000 elements is going to truncate the middle part when it's displayed. So I'm going to make my A range 1001 elements. And now when I do sine, I get three elements of the array and then some dots and then 3 elements at the end. And so it truncates it. That's what that threshold means. The other thing that I could have done would have been to move the threshold down, maybe set it to 100 instead of 1000. And let's just do that just for the sake of sanity. Okay, so I set it here. I re-execute this cell. Notice this is now cell 62. And if I come down here, well, it doesn't matter because it's over the threshold anyway. So there's a whole bunch of functions like that. If I just did NumPy dot, you can see I've got absolute value, arc cosine, arc hyperbolic cosine, blah, 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 blah. There's just a bazillion of these universal functions. Those are not all universal functions, but many of them are, and they're all designed to work they're designed to work in a fast vectorized way. Now it matters very much if I import the sine function and try to do the sine of A. Now I'm going to get an error because it says only length 1 arrays can be converted to Python scalars. Sine is looking for a scalar value. It's not able to work on. So the regular sine that comes from math is not designed to work on a vector. It's only designed to work on a scalar value, a single value at a time. So if I wanted to use this function on that array, I would have to set up the for loop, and I really don't want to do that. So let's remember not to do that way. So exercise 4 with vectorized functions, I want you to redo the computation of exercise 1 using ufuncs. So I just want you to create, so you'll create an x from minus pi to plus pi, and then compute the sine of x. And then check the speed of the computation using timeit. Let's see. And I'll set a timer here. We'll count down maybe 5 minutes. it's a pretty simple solution. Then we'll take another short break. Okay, so this one was pretty. So we'll just do x equals np dot lin space minus np dot pi to np dot pi, 101 elements, and then y equals sine of x. Was anybody tempted to use a for loop here? Yeah. It's a hard habit to kick. If sorry, if we do np dot sine. So the NumPy functions work on when I'm saying vectors, when I'm referring to it, I'm using vector as a when I talk about a vectorized function, I mean I'm using that interchangeably with the array, so it works on the whole array at the same time. So if we did time it np dot sine of x, and then right next to it we do time it sine of x for v in, no, sine of v for v in x. Let's just compare those two real quick. Okay, so just under a microsecond for the NumPy, and about, what, 11, 12 times slower in a for loop. Okay, any questions on the computations? We'll come back and visit this, but I'm going to have to introduce something about the shapes and array shapes and such, the array shape and structure. But before we do that, let's take a 5-minute break, and we'll come back after the break, and we'll talk about shape, structure. We'll get into dimensions, axes, and that kind of stuff. So let's take 5. Okay, how we doing? Everybody good? Ready to get going again? Awesome. Let's move on now. We've talked briefly about how computations work, and we'll come back and revisit that in just a minute. But I want to talk first about how the arrays work. So far, we've only looked at one-dimensional arrays. We've just had some very small kind of toy examples of arrays. But it turns out that arrays have shapes to them. And the reason it's called the ND array, that N stands for N as in it could be any integer, and D means dimensional. So the ND array is an n-dimensional array, and the NumPy array is meant to be generalizable to 1 dimension, 2, 3, 5, 10, 1,000, 1,000,000. So you can arbitrarily affect the dimensionality of a NumPy array. And it's meant to work without introducing a big overhead of, without introducing a big burden on the programmer to think through all of that. So let's start by taking a look at a NumPy array. Let's see. Okay, this wraparound right here is indicating that I need to go back up to my print options. Let's maybe make this 120, maybe 110. I want, what I'm aiming for is for the wrap to happen in NumPy and not in my Jupyter notebook. Okay, so if we look at this, I've just created an array with 24 elements using arange, and every array has an attribute called the shape, and that shape is a tuple. An attribute is it's a piece of data attached to a Python object, right? And I can read it, I can write it, and so forth. And so this a.shape is a tuple, and the tuple has, if I look at the length, it's obvious right now, but if I look at the length of the shape, it's 1, and that is the dimensionality of the array, right? So I've got 1 dimension, and the size of that dimension is 24. So I have a single dimensional array, and that the size of that dimension is 24. Now the neat thing about NumPy arrays is that I can manipulate the shape of the array without creating a new array. So I can just write to the shape tuple, and I picked 24 because it has a lot of factors, and so I can change that array into a 6x4, and you'll notice this will tell us something about how this is set up and how it's kind of held in memory. So the 0 through 23 on here, those are all contiguous and consecutive. And if I look on 6x4, you can see that that first element here, 6, refers to the number of rows, and 4 refers to the number of columns, and that the continuous, like the ordering of the array happens along the rows, right? And so if we think of this first thing right here, the 0 through 23, as being that's the order that they appear in memory, you can see that it's just been formed into rows, and the rows have been stacked onto each other. And so now I've got 6, which is the vertical dimension, it's the number of rows, and 4 is the columns, that's the horizontal dimension. And then I could expand this if I wanted to into a 3-dimensional array, and now I'm going to do a 2 by 3 by 4. And what I get is I get a 2, and you'll notice that the 2 is like 2 whole pages. And so the 2s are a little bit like, think of them as being in back, one in back of each other. And then the 3 refers now to the vertical dimension, the rows, and 4 refers to the number of columns. And so all of a sudden we realize, okay, we've got to do we need to memorize something. We need to figure out a way to keep track of which of these elements refers to the rows. And you can see that the row is always 4, and that was always the last dimension. And so I've got a chart here, and you should have a copy of it too. And a couple of people have pointed out to me that I did, in fact, make a last-minute update. I made a late update to the notebook, and so if you may need to update your repository to get all of these. This one should be in it. I think it's just the big ziggurat is the one that I added this morning. But you should have a copy of this. And so I'm going to walk through this and kind of explain it a little bit. In the example above, in a single dimensional array, in a one-dimensional array, there's one dimension, and that's considered to be the 0 dimension. Remember, in Python, we start counting at 0. And so if I have a one-dimensional array with 4 elements, its shape tuple is going to look like 4, and 0 will be the only direction. And for the sake of space, we display it going horizontally on the screen. By the time we add a second dimension, now 0 is pointing down. So the lowest order dimension is pointing down. And so I'm going to come back to this again and again as we go through it. But the 0 axis points downward on the screen, and that has 2 elements. And so this makes sense if you think about it in terms of rows and columns. So row, comma, column. And and so I have a 0 and a 1. So this is the 0 dimension and the 1 dimension. By the time I add a third dimension, 0 now points into the board, and you can see that as I add each dimension, it turns out the one that's changing is always the 0 dimension. That's the one that's changing. And the highest order dimension is the one that stays constant, and that's the rows. And I'll make a point with that in just a moment, but now I've got 3, which is into the board, 2, which is down, and 4, which is across. And with a 4-dimensional array, it starts to get a little bit harder to wrap our heads around a 4-dimensional array. But I've got a 3-dimensional array and then another 3-dimensional array. And so we're kind of showing the 4th dimension that way. So as you remember from indexing, if I think about this as dimensions 0, 1, 2, and 3, if you think about indexing, we can also use negative numbers, right? We can think about this as being -1, -2, -3, -4. And so sometimes it makes a little bit, it's a little bit easier to think about them in terms of the negative. And you'll see that the highest dimension is always the row. And the row is the one that has the shortest spacing between the elements. So I'm just going to come back up here and show you on the example that we had on line 71. We have the one-dimensional version, and the shortest distance between the elements always occurs on a row, right? And then when I changed it into a 2-dimensional array, I've got dimension 0, which has 6, and dimension 1, which has 4, and the shortest distance between elements is still on the row. And then when I changed it into a 3-dimensional array, the same thing happened. So now dimension 0 goes from here to here, from 0 to 12. And then for dimension 3, I'm going from 0 to 4. And then for dimension 3, I'm along the row, and that's the shortest step between them. Does that make sense? I find that this may be a good thing. sometimes I have these Post-it notes, and I may stick one of them up on the wall just to. Actually, I'll go ahead and do that because it's handy. But this is a good diagram. Like if you're doing things that involve array shapes, it's a good thing to have this kind of sketched out somewhere. So for one dimension, this is 0. And for 2 dimensions, we've got 0 and 1. And for 3 dimensions, yeah. Don't know if y'all can see that very well, but I'll just kind of leave it up there so that you can see. Maybe I'll go sideways on the marker. So that's going to be useful in a little bit when we start to work with arrays that have greater than 1 dimensionality. For the most part, a lot of what we do is just work with 1 and 2 dimensional arrays, and I'm not going to get too much into 3-dimensional arrays today, just because conceptually our brains don't work that way so much, and a lot of what we deal with is just in 2 dimensions anyway. But there are many use cases where you have higher dimensionality of your arrays. Anyway, so you can keep this diagram kind of around. I don't know, maybe print it out or copy it or something like that. But it will help you to kind of recall which direction you're thinking of. Now, one of the things that I know that sometimes comes up, and some people start to think about this as being like a row vector, or it's important to remember that this is that you have to look at the shape tuple to understand the dimensionality of the array. Maybe I'll just leave it at that. The last thing I want to point out to you though is that sometimes it's helpful in determining the dimensionality of the array if you just look at it to count the number of square brackets. So on this 1-dimensional array, I just have a single square bracket, and NumPy uses square brackets to indicate the different dimensions. And so here I've got two square brackets opening, and that is an indication this is a 2-dimensional array. And then on this one here, I've got 3 opening it, and so that's an indicator to me that this is a 3-dimensional array. This subset right here is a 2-dimension, and so forth. So this is how we display them. And the thing that is fixed about it. Oh, no, I don't want to do that. Never mind. The thing that's fixed about a NumPy array is the number of elements. So I can't change the shape tuple. I can't write to a new shape tuple that doesn't have the same number of elements. And so if I wrote a shape tuple that was 6 by 5, that would have 30 elements, and I've only got 24, and so I would get an error on there. So the number of elements of an array is fixed. Now, I do want to point out, though, that we can introduce arrays of higher dimensionality. So let's look at the array shape right now is 2.3. And if I wanted to turn this into, I'm just going to reset this to, let's do like this. Now, in this case, what I'm getting is an array that is a two-dimensional array, but one of the dimensions is empty. It's what I would call an empty array, or just a length 1. So this is what you might commonly think of as a column vector, because it's a two-dimensional array, and all of the data is organized into a single column, and that is and similarly, a thing that you do sometimes would be to have a like a row vector, right? So this is a two-dimensional array, but it's all in a single row. And I'm going to show you a little bit later. There are some operations that we can do between arrays of the right shape that allow us to repeat elements of the array in each direction. I'll come back to that in a little bit. I want to also introduce the notion here. If I type a.reshape, notice that it returns something to me. I get a new object back. So if I say b equals a.reshape, I now have b as an array that has the same data in a different shape. But watch what happens if on A or on B, let's see, have I talked about indexing yet? Okay, I think I need to talk just briefly about about indexing. I think I missed a part here. Okay, so if I have an array that has multiple dimensions, I've got different options. So if you look at B, it's a two-dimensional array. It's a 2x12 array. Now I can index into this array using comma-separated indices. So B0, comma 0. 0 is the index into dimension 0, and this would be the index into dimension 1. So 0, 0 is obviously that first one, and we could say 0, 5, and it would be this element right here. So I can use a comma-separated list of indices. If I index into an array and just specify a single value, what that does is it indexes into the lowest dimension. So B1 is going to apply along dimension 0, which is the vertical dimension, and I expect to get 12 through 23 when I type this one right here. Okay, so an omitted index just means that I get everything from it, right? So that's a way of pulling out a row of the data. Now watch this. If I do B1, so now when I'm doing B1, well, okay, I'll start by showing the getting and setting. So if I set B00 equal to minus 99. And then we print out B. You'll see that there's minus 99 there. Now notice that when I look at A, it changed on A as well. And that's because there is an idea in NumPy arrays of having different views of the same data. And this is a really, really important concept. When I call a function like reshape, or when I do slicing, like I'm going to show you in a little bit, what I'm getting is a different view of the same underlying data. So this reshape returns the same data in a different view. It's just a different way of looking at the same thing. So for example, I should be able to do b.1 fill with zeros, and then b, and you can see that I'm referring here to that whole second line, and I just filled it with zeros. And so this shows you different kinds of manipulations that are going on here. Did I just lose anybody? No? Okay, question? Yeah, and so if you look, the second half of A is all filled with zeros, even though it's, yeah. Did you find a thicker marker? Thank you. Logan's a real hero. Okay. Okay, so I want to take a moment now and talk a little bit about what's going on behind the scenes. This is a diagram that I borrow out of the material that I teach that kind of helps explain what's going on here. We've seen that when we create an array, a certain number of values get allocated in memory. They get created as a memory block. And in Python, we might have created this thing as a 3x3 array, but we know that it didn't allocate in memory. There's not like some little square in there that represents that memory. In fact, in memory, it all appears just in a long line. And in fact, I'm not actually being entirely truthful. There are so many layers of abstractions in how memory works. But the useful abstraction for us is to think about the computer memory as just existing in one long line. I know there are many, many ways to think of it. But but at the most useful abstraction for this, we just think about the memory as all occurring in a long line. And so each position in memory has an address, and that address is basically how many, what is the number of bytes that I have to use. And so each array has a memory block. It has a set of values that represents the actual data, but then it has some metadata or some descriptive data that describes how we're going to interpret it. And for NumPy's purposes, one of the most important is the D type. And so int64, for example, means that I need to allocate, right, it's going to take 8 bytes to represent a single number, and then I'm going to do some kind of a numerical conversion of the ones and zeros into an integer value that takes 64 bytes. Probably, well, we can't go into it, but there's different ways that these get represented. Are they signed? Are they unsigned? Do they use one's complement or two's complement? There's a lot of different ways that the ones and zeros get interpreted mathematically to make it work. And it's important, the details are important, particularly when you have, when you're trying to understand something on disk, for example, the D types are important. So you've got int64, for example, that will represent integers with positive and negative integers and so forth. And that describes how do we interpret the ones and zeros that constitute this particular element. And it also describes how large is each element. There's another piece of this, which is the ndim, which is the number of dimensions. And that says how many elements the shape and something that we call the strides tuple are. And the shape just describes, I mean, we've talked about the shape, and I think y'all understand what the shape is. But the important thing here is that the shape allows us to compute the strides. And the stride is how far do you have to go in memory to reach the next element of the array in a particular dimension. So if I have a 3x3 array, and I want to move from 0 to 3 along axis 0, right? So I want to move one element along axis 0. So that would be the distance between 0 and 3. The strides tells me I need to go 24 bytes in memory to get from here to here. So I go 8, 16, and then 24, and that lands me at element 3 along that dimension. And if I want to go, if I want to move in one element along dimension 1, then I look up in the stride tuple and I see in dimension 1 it's 8, and so to move from 0 to 1 I move 8 bytes. And so the strides is how NumPy knows how far it has to move in memory to find the next value in that array. And this is the key to making the computation fast and efficient. And so when I'm manipulating the shape tuple, there's just a contiguous block of memory, and I'm just describing a new way of presenting the data that has a shape and it has a particular number of strides. You've got a question? Yep. Does that make sense? And so, and you've got a question? It depends. So a float 64, because it's using 8 bytes, would have the same strides. But a float 32 would have strides of half the size, or a float 16 would just be 2 bytes per float. And so it depends on the details of the D type. And there are some things like Boolean values that are just those are represented by a single byte. Okay. Yeah, so this is really the magic of the NumPy array, is the idea that you can create different ways of looking at the same data and running through it. Yeah, just by a simple manipulation of the shape and the stride. So let's do some live coding examples. The one that you see on screen just looks like this, right? So I've just created here A is equal to 0 through 8. And if I change it into a 3x3, like this, you can see I've got the same representation as in the diagram. And now I've got the strides being 24 by 8. Now, yes, go ahead. Oh, fantastic question. So a dot shape is that is an attribute of the NumPy array. And if I write to that shape, then I'm changing the shape of the array A. If I do a dot reshape and then give it a new shape, I get something back. I get a new array object back that is looking at the same data, but is has a different configuration, a different shape configuration. And let me show you, for example. So if I do b dot, oops, b equals a dot reshape. Nine comma 1. Now it turns out that NumPy has a function called shares memory, and you can use it as a test to see whether A and B have memory in common. And so that would be a pretty important thing to keep in mind. And I was having a conversation actually over breakfast with a couple of guys who are from the MathWorks, which I thought was really interesting. So MATLAB is kind of a, I don't know, maybe it's a frenemy of NumPy. They work together, but it's often kind of a competitive kind of situation. But one of the big distinctions between MATLAB matrices and NumPy arrays is the convention here. So this ordering in which the shortest stride occurs on the rows, or the shortest stride occurs on the highest dimension, that's called row major ordering, and that is the convention, that is the style of array that C uses for computations. And the convention is different in Fortran. In Fortran, you have what's called column-oriented arrays, and in a column-oriented array, the shortest distance between strides is always along the columns. In other words, it would be on the lowest order dimension. And switching the arrays between what's called C-ordered and F-ordered orientation is one of the big things that you have to work out between working in MATLAB or in NumPy. It also comes up in NumPy sometimes, because I'm going to go back up here to the ziggurat, and you remember that I mentioned here that NumPy is based on CPython, but it's also based on Fortran. So there are parts of NumPy that come from Fortran, and much of SciPy comes from is Python wrappers around Fortran. And Fortran codes tend to produce arrays that are column-oriented versus NumPy, which has them row-oriented. Now, for the most part, you don't have to worry about this. NumPy will just typically do the right thing, and you don't have to worry about it. But there are times when you are pursuing some performance, or you're up against a performance bottleneck or something like that. And it's helpful to understand, what do we mean by C-style arrays in which the shortest distance occurs across the rows, and Fortran-style arrays in which the shortest distance occurs across the columns. And so that's a thing that can come up. And you might encounter it, and you might not in your career. So I think I was showing you about the shape and the strides. And one of the things that's really nice about this, and that NumPy does really well, is, let's say that we wanted to get the transpose of this array right here. One way to compute the transpose would be to make another array block and then just do the point-by-point copying. And that would be really memory intensive. And for example, I think that's what MATLAB does. And so computing a transpose in MATLAB can be very expensive computationally. In NumPy, it's trivial. So the transpose is it's an attribute of an array, so you can just do a dot capital T, and that gives you the transpose. And so now I'm doing B, I'm creating a new array B, which is the transpose of A. And so what used to be a row in up on output 90 is now a column, right? And so now I've got column major ordering, or column oriented. And the way that this is accomplished in NumPy is just to roll the stride tuple. That's all it did to compute the transpose. And so it's a trivially simple operation and computationally very fast to compute a transpose, because all that you're doing is changing the strides. Now, I want to point out on the NumPy array, there's something called the flags that you can take a look at. And the flags will tell you, is this contiguous in terms of C orientation? In other words, is it contiguous along the rows, or is it contiguous along the columns, as in Fortran orientation? So A is C contiguous. A owns its own data, and so on. And if we look at B, we'll see that B is not contiguous along the rows. Rather, it's contiguous along the columns, and it doesn't own its own data. So this is another way of seeing, okay, this is the one, this is the originator, like this is the this is the original owner of the data, and B is looking at somebody else's data. The own data is false. Incidentally, if you want, you can, I think what you do is you look at these as if they're a dictionary, if you want to check. And you'll get it like that. Okay, so that's kind of this array data structure. Are there questions on that? Does it make sense? Go ahead. It tells you that if you're about to write to this array, that it may change it somewhere, some other place. Yes. Oh, okay. So, are you talking about all the flags and the contiguous? Okay, so reshape creates a new Python object, which is a NumPy array that has data that doesn't belong, that belongs to somebody else. Yeah, yeah. And there are other ways. So so there is np.copy, where you can explicitly get me a copy of this array. Let's see, a dot reshape I wonder if it's NumPy. Some of these have a copy equals true. No, I think you have to explicitly ask for a copy if you want a copy. And the reason that this isn't top of mind for me right now is that pandas use it. We've all heard of pandas. Pandas is very copy happy. It makes a lot of copies of new things. It manages to do it efficiently for the most part. NumPy tries to create a view when possible, because because copying memory is time consuming. It takes time, and it's a tax on the computation. And so NumPy in general tries to get away without copying data whenever possible. Go ahead. Well, yeah, okay, so the question is about Yeah. Okay, so I think there's a couple of things there. So you're wondering about, I think you're wondering about the difference about creating a new view of the same array. And that is relatively efficient. That's cheap. To make a new view of an existing array is an inexpensive operation. If you were to copy the whole array for each instance, if you had a whole bunch of classes and they were all using the same data, copies would be expensive and it would quickly run you out of memory. And so the ideal thing to do would be to make it just a new view for each of your instances, and that would be pretty lightweight. I can't tell you exactly what the memory requirements are, but I think you can look at what it there's in the system module, in the sys module, there's like a get size of or something, and you can see what's the size of a new object. NumPy arrays are not large themselves because get size of is just looking at the metadata part of it. It's not looking at the data, not at the data portion. And if you wanted the data portion, you could look at the n bytes and see, okay, this one uses 72 bytes. Get size of array. And that's I think that returns bytes also. And so I think that this is constant relative to the size of the array itself. And then this is going to scale with the size of the data portion. Question? No, because B still has. I haven't picked a subset. Well, I'm going to get to a point where B might have a smaller memory footprint. But let's get to that. I'll just move on first. Anything else though on this? Go ahead. Mm-hmm. No, because so there is one thing that can happen, but generally speaking, you're not allowed to create a shape that you won't be able to create a shape that that violates, like there's restrictions on it because it has to have the same number of elements. One of the things that can happen is there are ways at looking at your data. So you can look at your data as if it were flat, and if you did b dot flat, so you can kind of get a little bit tangled up. So flat is going to do it in the order of the rows, like according to the NumPy convention. It's not going to return it as it exists in memory. There is a let's see, there's a dot flatten, which will give you, I think this one gives you a copy of the array. And I think this one maybe, ooh. So I think flatten always gives you a copy, and then there's yet a third one called ravel that tries to be efficient if it can. So between flatten, and ravel, you've got three different priorities. Flat always gives you a view because it's an iterator. Flatten always gives you a copy, and ravel tries to be efficient when it can. And so I guess the thing that I'm thinking of is that the difference here is that this result A dot ravel is a view and B dot ravel is a copy because these are not contiguous and these are. Logan, did I get that right? Do you know? Is that? I think we're a little bit in. Yeah. Let's do np dot shares. Yeah, we looked at that already. So A dot. Yeah. So this is the one case where, and it's not really like it's you were asking if you could get into trouble like by, I don't know, twisting it or something. Like you can't corrupt the original data, but the thing that happens here is that because this is no longer contiguous in memory when you're looking at flattened views, that's the one thing that I can think of where you might end up in trouble. Generally speaking, though, that's not problematic. Let's see. We're going to get on to loading data, but let's take a short break now. I think I'm going to set this one on 3 minutes. Just like let's get up and stretch because we're coming into the final stretch. When we come back, I'm going to talk a bit about how do we get data out of files, because we almost never only just make up our own data. Typically, we're reading it from files. And so when we come back, I'm going to talk about loading data from files, and we're going to do a couple of exercises. And I hope this will maybe kind of create some motivation for you to understand, to want to learn about pandas. So let's take a 3-minute break. We'll come back. Okay, we ready to get going again? I'll give us just a minute to get back to seats. Okay, in NumPy, like I said, very often to look at data, we need to load it from a file. And I've heard it said before that, I don't know, I'm not sure what the percent. It's certainly not the case anymore in the day of large language models, but there was a time maybe 10 years ago when you could reasonably assume that, I don't know, 50% of compute cycles were converting between ASCII and binary formats, like reading off of, reading from text and converting to a binary format. NumPy provides a pair in particular of functions for reading text files. And one of them is called load text. And this is kind of your workhorse. It is the first thing that you want to try, and it's good for a lot of different things. And I've got the docs here. If I right click, enable scrolling for outputs. And so that shows you the doc string. And I encourage you to, at some point, spend some time looking through here. But I'll point out right now that the main thing that you do is you give it a file name, and then you can optionally specify the data type that you want. You can tell it what kind of things count as comments, what are the delimiters. You can convert particular columns by specifying callable functions to use to convert a column. You can tell it to skip rows, to use columns, et cetera, et cetera. There's a lot that's there. And so load text is pretty capable, and it has a lot of, like for some particular format, if you look, there are some fast pathways for optimized loading of data in particular formats. So I've given you some sample data to play with a little bit, and this comes from one of my training courses. And the data, if you click over, so let's open up the folder icon and get this and click into the data folder. I've given you one called Wind Simple. And if you're interested in where this comes from, it's public domain. This is a study of a wind that was done in the 60s and 70s in Ireland, and there are 12 different stations throughout the island, and the data is formatted as just white space separated. These are actually fixed columns here, and so you've got a column for the year, for the month, for the day, and then the wind speed in knots at the 12 different stations. So every row contains 15 values. And so if we just throw that into np.loadText, and look at the first 5 rows, I need to go back up and set my print options. I didn't get them right. Okay, my print options, I'm going to set them to maybe 120. All right, let's come back and look at our load text again. I think though that that's a window wrap. Okay, so you can see here what's happened is the wind data here has loaded. The year column should be a 2-digit integer for years. The month should be an integer, and the day should be an integer. But remember what we said about NumPy arrays, that every item in the array needs to have the same data type. And so what this did was it read in the data and it coerced it into floating point numbers, which is okay. We can work with this data in floating point format, right? It's fine if you have a year that's 61.0, because we know what that means. And if we need to work with the year at all, then we can do that. But remember how I said that there's the ability to. Okay, so let's just celebrate the fact. Wow, we read in a large data set, right? I mean, it's kind of cool. It did that really fast. Let's see, data dot shape. I mean, it was really fast when it read in there, and it's, 6,500 rows. So, and the D type is all float 64s. So what would we do, though, if we wanted to get this in? Like, one of the tricky things about NumPy is this requirement that every element in the array have the same data type. And in fact, a lot of real-world data is columnar data, where the columns are all have the same data type. Like, the data is consistent, it's homogeneous in a column, but not across a row. And so NumPy deals with this by letting us do something called a structured array. And so we can work on the D type and build up what's called a complex D type, or a structured D type. And the way that this works is I can make a list of tuples, and each tuple, actually NumPy allows us to kind of to build up a structured data type, and it has multiple elements to it, and one of which is to specify that every element of my array. So what I'm planning to do here is, instead of having a 6574 by 15 array, I'm going to make each row into its own element, but each element is going to have a subsection. And because those are all regularly sized, I can still compute the strides, but now each element is going to have 3 integers and 15 floats. And so that's what it's going to look like, and this will end up with a little bit different kind of array. And the nice thing is that when I'm creating this structured array, I can also assign names to the subfields. So the first thing I'm going to call the year, the month, the day, and each of those is going to be an integer. And then the last one is called wind, and that's going to be a float with 12 elements, right? So I've got a list of tuples, and the tuples each specify what the D type of that particular element is. And then, so I've got 3 of them here, and then I've got the last element, which is itself going to have 12 elements. And so I can build up a whole structured D type. Question? The reason I picked 12 was because there are 12 measurements here. I think that's right. 1, 2, 3, 11, 12. Is it 12 or is it 13? 6. Yeah, it's 12. So, yeah, so what I'm doing here is on this array, each number is its own element. But now I'm going to build up what's called what you could think of as a nested element. And so now each element of the array is going to be nested. It's going to have kind of two layers. There's going to be one layer, which is the year, month, day, wind, and then wind itself has 12 sub-elements. So I can build up a D-type like this and then specify that for the D-type. And now you'll notice that I've got columns for the year, the month, and the day. And then I have another element here. So if you look, it's a one-dimensional array with a single square bracket. And then each element has four pieces to it. It's got a year, a month, a day, and then a wind component. And that wind component itself has 12 elements. Now the nice thing here, let's do, so I'm going to type in data.shape. And so you can see it's all now a single column, or it's a one-dimensional array, but it's got this built-up structure. And so I can look at data dot, or and these appear as if they are, I can access them as I would a dictionary. So I can look at the years, or I can look at the wind component. And now the wind component itself is a two-dimensional array like I would like to use. So let's see. I feel like maybe are y'all with me so far? Is this working? Okay. So there's data here. I can pull out the wind, and if I wanted to, you won't be surprised then to say I could do. I could pull out just the wind portion of it. And now I have wind, which is a view into this other data array, right? But I can use wind as if it's a normal NumPy array. Go ahead. It's a little less elegant than how Pandas does it, because the nice thing about Pandas is that the nice thing that Pandas does is to take this year, month, and day and turn it into an index that you can use to kind of line things up. And in this implementation, you wouldn't have that. You wouldn't be able to look up your data by date. So Pandas has the better solution to this. But NumPy, the nice thing about this is that this gives you kind of low-level access to what's going on. So, for example, if you look up here in the wind description, and you look on the Fortran format, it tells you integer 2, integer 3, 12 float 6.2. If this were a binary description, you could design your NumPy D-type to match the format of the binary data, and then just read it directly into a NumPy object, which you could then hand off to Pandas. And so understanding how this works in NumPy at that kind of level can be really helpful. In my 12-year programming career for scientific computing, like doing this kind of thing, I had one project where I had a binary format, but it was knowing how to do this was the key to making that work, and understanding about the structured data type was critical. So We're not going to dwell on it too much, but I am just going to, because this is a NumPy tutorial and not a pandas tutorial, I'm going to talk about this. So I do get to look at my data like this, and I've got the, I can create a new view, right? So wind equals data wind. That will give me a new object that is a view of that portion of the data, and I can work with it like any other NumPy array. And so if we looked at the year, that would be the same kind of thing. And the nice thing now is that the years are integers like we expect them to be. I want to point out maybe too that in int64, we don't care that much about memory now. Like the fact that this is an int64 and I really only have to span a small number, I really don't need a 64-bit integer for that. So I could come and look up in NumPy, and I could look up in the NumPy data types. There's a large collection of data types in here, and I could find, oh, there's an 8-bit integer, and maybe that's enough for what I need to do, right? And then I could save some memory. Chances are I really don't care about that in laptops that have gigabytes of RAM. It's just not an issue anymore. But you could come back through here, for example, and do a NumPy int16, for example, and reduce the data footprint of that, reduce the memory footprint of that component, because the year is just, it's never going to exceed 255. I could even do an int8. And so now I've managed to save some memory. Okay, so that, for example, is is how you could load from a file. Now that I've got a nice two-dimensional array with something actually meaningful, let's talk about computations. I want to come back and revisit the computations. NumPy, among the universal functions that it has, are a class of functions that we call reducing functions. And by reducing functions, I'm talking about the kind of function where you take a number of values and you reduce it to a single value. So a mean would be an example. I have 15 values and the mean has a single value. And so I've reduced the size of my data from 15 to 1. And so the NumPy has these reducing or reduction functions. And the default, when I call that, is just to provide a global, it will reduce it by default into a single value. So if I look at the mean wind speed across all of the across all of the stations and across all of the dates in the period, I find out that there was a 10.228 knot mean wind speed across all of the data that we had. If I wanted to find an average per site, per location, so remember we've got days on the vertical axis, and so I'll come over here, and this is where it's helpful to have the axes in mind. So the days are along axis 0, and the locations are along axis 1, right? So days are the 0 axis, and locations are axis 1. And so on all of these reduction functions, I can specify an axis that I want to reduce. So if I reduce axis 0, I'm left with something in the shape of axis 1, right? So if I specify axis equals 0, that's going to sum up, or it's going to mean average or compute across all of the days and leave me with a result that's just the locations. So I could do the same thing here. I could do wind.mean and specify axis equals 0. That represents the days. That's the axis that's going to disappear. And so now I'm left with an average wind speed at each location. And I could see that, oh, this is my windiest average location, this one here, and this might be my least windy. Now, if I wanted a daily average, then I would collapse the other axis. I would collapse axis 1. So axis 1 is the location. So now I'm averaging over all of the locations, and I'm left with one value for every day. And so this is a long array that has the same number of elements as the days. So for example, if I wanted to plot, I could plot that value. We could just see what is the plt.plot. And that's the daily average over the course of the whole experience, the whole measurement exercise. So in addition to mean, there are things like the maximum value, the minimum value, the and the peak to peak, various things like that that will reduce or aggregate. I want to point out, for example, there is the max function, and this will report to us what was the maximum wind ever, for example. And then there's something called the argmax. And I'm going to start with argmax by, if we did wind.mean and let's specify axis equals, so I want to collapse all of the locations. So I'll collapse axis 1. Argmax reports not the maximum value, but the location or the index of the maximum value, right? And so what this does is it tells me that it was on location 2160, right? And so if I was to now say data 2160, I could use that and it would return to me, and it says, okay, that's 1966 on December 1st. Not surprised that early December is the windiest day, and you can see a lot of high wind speeds right along there. So load text gives us the ability to pull in a simple file like that. The fact is that sometimes we end up in situations where there's more complexity, and so we need a little bit more power. There's another function called gen from text, which gives us a little more flexibility. It's also more complex. And if we look at wind.data, so we were looking at wind simple, which is the easier one. And if we look at wind.data, this one's a little more complex, and you'll notice things like it's missing a row at the top. There's a line that has header information that we might want to use, and then there are some missing values. And so this is NaN is it stands for not a number, and it's a way we need to turn that into, somehow indicate that that's a missing value. So NumPy has a let's see, I'm going to maybe pop over here and just kind of show you that NumPy has a value called np.nan that it uses, and this is not a number, and it's used to represent missing or invalid data. So let's do a short exercise here. In win.data, there's a blank row, a header row, and some missing values, and those missing values are shown by the text nan. So gen from text has more flexibility. It has something called, let's see. It has something called skip header. It has names, missing values. I would like you to look at the docstring for gen from text and create a wind array that just has the wind speed measurements. So you can reuse the D type from before. The main thing that you'll need is skip header. You can look at names and see what that does. I suggest that, I don't know, let's give this one about 10 minutes, and I suggest that you start by doing np gen from text and just take a minute and look through some of those things and see if you can use that function to load the win data file. There's more than one way to do it because the fields are already named in the D type. You don't have to use names, but you can take a look at that one and try to use it. So let's take a few minutes to do this one. And you can get some practice on your own. All right, y'all ready? Ready to move on? We good? Okay. Okay, so there are a couple of, maybe two different ways to do this. One with the, one using the names feature and one not. So the main thing that we're doing here is just using the skip header. I wanted you to take a look at gen from text just to kind of see what's in there. We didn't have to use the names feature, but the names feature is kind of something that gen from text has that load text doesn't. So we can do it without it, and we can load the data. You can see the main thing to point out here is that now we have nans interspersed, and that worked. I don't think that load text would do that. And setting the wind from the data was just a simple matter of referring to the field name and the structured data type. Alternatively, you could use the names equals true, and if you look in the docs, what that means is names equals true will take the first row that's not skipped, and it will infer field names from that header row. So in this version here, we're skipping both the blank row and the header row. So skip header equals 2. In this one here, I set names equal to true because I wanted gen from text to parse the names, and that means that we need to only skip one line of the data, only skip the blank line, and then we can apply the d-type. The thing to note now, though, is that the field name, it used the first value of, it used this as the first value instead of wind. So if we want, so we can look at the data d-type names and we can see what they are, and instead of being wind, it's called RPT, which is the name of that location. Are there any questions on gen from text and loading? Okay. I saw a number of you had some things you were figuring out while we were going. So I've already talked about missing data a little bit. We've got wind that contains some nans. I'll just point out to you that if you include a computation that has any nan value in it, any nan value will cause the whole result to be a nan. And so NumPy philosophically has the idea of maintaining purity. If anything is missing, then the whole thing is missing. So it's never going to compute a value if any part of it was missing. That is distinct from pandas, for example, which will by default just ignore missing data instead of disqualifying or propagating it. If you would like to ignore the missing data, NumPy has a set of functions that start with nan that you could use to compute the data that ignores the missing values. And so I use nan mean to compute the missing values. I'm sorry, I use nan mean to compute the mean value, and now it's ignoring the missing values, and so it's not including those at all in the computation of the mean value. So are there questions about loading data, about missingness? Yeah. 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 But I did just know it. So if you come up to there's a substantial section of the of the NumPy documentation that deals with creating your own custom D type. And you can look in here. Maybe what I'll do is, well, I have a link to this in the notebook, in the section on D types. That's a link to that section of the right here, the NumPy docs. So you can look there. But yeah, that's kind of, I hope that maybe that's one of the advantages is coming to a tutorial, because it's easier to find out about that than searching through the docs. All right, thanks for the question. Anything else before we move on? I wonder if, oh yeah, go ahead. Yeah. Yeah. Okay. Yeah. Yeah. So, the answer is yes. There are ways to deal with that. Can I name them off the top of my head right now? No. But yes. And so fixed width column is a thing. That's a fixed width format. FWF is a thing. It's a standard way that things are dealt with, and you can work with it. It may not be NumPy. You might have to do it from pandas. May have a better reader for that. But yes, there is definitely a way to deal with that. And there was also another question about if you have some custom binary data format, you can use a D type, a structured D type to read a custom binary format from disk in the same way. So just as we've done load text here, you can also read directly from a binary file. If you know the binary format, you can construct a D type that matches the binary format, and then just use the NumPy load and specify the D type, and that can load a binary format that way. So that is certainly a thing that can be done. There's all different kinds of ways to do it. Go ahead.
What does the missing values property actually do? Because I was playing with loading this file, and it seemed to auto-detect the nans that were missing.
Yeah. Yeah, so in gen from text, it has there's a list. If you go far enough into the documentation, you should be able to find kind of a predefined list of things that it will interpret as nans. And the reason that there's something on there is that you can also specify your own custom missing values. So for example, in the world of geophysics, there are these custom values, like I think it's minus 999.25 is the indicator for a missing value. And so you can specify that as the NaN value, and anytime it finds a minus 999.25, it will interpret that as a missing value. So I want to talk a little bit about the slicing and the dicing, and I've covered some of this already. Slices in NumPy, they work in very much the same kind of way that they do in Python, in pure Python for lists and so forth. So I can take my my data and I can slice it. And the slicing works. We start at the lower end, we end at the upper end, and we go up to but not including the upper index, and we advance by the number of the step. So for example, if I start at the beginning and go up to but not including row 10, stepping by 2, I should get 5 rows here from the win data. Because I just specified a single dimension, as we said before, that applies along dimension 0, and so I get something in the shape of it'll give me everything along the rows. Unlike in pure Python, because pure Python doesn't have Python lists don't have the idea of multiple dimensionalities. there's not any such thing as multiple indices, but you can do multiple indices in NumPy using a comma. And so here I can apply a slice along dimension 0, and then I can apply another slice along dimension 1, which would be the location. So this would be every other location. And so I would start at the beginning, and I would get every other one. So we can see what that slice would look like. So instead of having 12 locations, now I'm just looking at 6. So one of the interesting things here is that slices are views into the array. So just as I created a new array object that was a different shape on the same data, a slice, I can create a slice, and it would be a view into the array. And changes in a slice affect the original data, just as they did on any other kind of thing. So for example, if I create a new array called first 2 days, which is the first 2 rows of wind, and then I fill those with zeros, and I look back at the original data, you can see this slice right here, this bit has been carved out. Right, it's all been set to 0. And so this being a view can actually lead to some efficiencies in computation. I've already showed you about the shares memory, and that just shows you that I've picked out a subset. The use case in computations is that you can do some really interesting kind of computations using slices. And this is one of the things that that makes it really once you learn to think this way, and once you learn to pose your computations this way, it can be really fast and efficient. So let's start with the wind data, and we'll just plot like the daily average. I just did the wind mean on axis 1, so this is the daily average right here. If I wanted, for example, to look at what was the change from day to day, right? If I wanted to do the inter-day change, I wanted to look for every day. I want to compute, okay, what was the average wind speed on this day minus the average wind speed on the next day. So one way to do that would be to set up a for loop and go through and compute for each one. But as soon as you learn how to do this in a vectorized way, then it becomes really, really pretty amazing. I wonder if this will work. Okay, I'm going to do my very level best not to draw on the actual whiteboard. So let's imagine that we have an array that looks like this. And it's got elements in it. And my job is I want to compute the difference between subsequent elements. And so the way that I had just mentioned to do it would be to do a for loop and go through it. But the fast, efficient way to do it would be to make one slice that has these pieces, and then one slice that looks like this. Okay, so I refer to this one as my forward slice. I refer to this one as my backward slice. And now, so if this one is 0, 1, 2, 3, 5, 6, and 7, so this one has 1, 2, 3, 4, 5, 6, and 7. This one has 0, 1, 2, 3, 4, 5, and 6. So if I take my forward slice and my backward slice and let's line them up right under each other, I now have 1, 2, 3, 4, 5, 6, and 7, and right under it I have 0, 1, 2, 3, 4, 5, and 6. So each of these is a slice of the original, but they're shifted off from each other. And if I take this one minus this one, then I get the differences. And I can do that in a single slicing operation. I'm not creating copies of the data. This is a very fast vectorized operation. Let me show you what that looks like on the wind data. Sounds like everybody else is winding up. we might go over. So the way that I would do that here was if I wanted to compute daily changes, I would take my daily average, so 1:0. Get the mic. So 1:0 right here, 1:0 is this one. Start at element 1 and go all the way to the end. I'm sorry, not 1:0, just like 1:. And then daily average :-1. So I start at the beginning and I go to the end -1 like that. And then that becomes my simple difference plot right here. So this difference computation is quickly and trivially done because it's that fast vectorized operation. No for loops involved. If you did a for loop, then it would probably, in this case, you're looking at something like 100 times slowdown if you introduce a for loop. Versus if you learn how to think kind of in vectorized mode, then you could speed that up a lot. I have a little example here just to kind of show you, and we're short on time, but I think this one is worth it. This will just kind of give you another example so you can kind of triangulate on it. I did something which was to read in the plot about the NumPy axes, and I just kind of reduced the size of it to get the computational time down. And then Matplotlib has something called image show that you can use, and I'm looking at it here. And there's a certain kind of operation that you can do on pixels where you average each pixel in an image with its nearest neighbors up and down. So it's called a 5-point stencil average. And you can think about this in the same way. If I want to take each pixel and average it with its up, down, left, right, and self, then that's the same kind of operation. And if you thought about it in terms of slicing, you can do that kind of stencil filter like this. So I have an image, and I'm which is a 2D array, and I'm going to take my up slice, which starts at the top and goes down. So along dimension 0, I'm going from the beginning to -2. And then I'm taking a middle slice, so starting at 1. I'm leaving off a pixel on either edge. So that's the up. And then down starts at number 2 and goes to the bottom. The center is just kind of all the way through it's 1 to -1 and 1 to -1. Left is the center on the top to bottom, but it starts at the beginning and cuts off 2 on the right-hand side. And then the right-hand side does the other thing, and I can divide it all by 5. And so this is what it looks like in vectorized form. So I could do that kind of filter, and if I want to time it, I'll just show you. I'm trying to make my point here, and I'm out of time, but we do the time it here, and you'll see it took about 45 milliseconds to do this kind of filter on that image that I just showed. Now let's compare that with the nested for loops, because these images are actually 2D images, but they have three dimensions deep with red, green, blue, and transparency. In any case, that's why I have 3 nested for loops here. And so this is if I was to go through and do the whole same thing in a nested for loop, and let's just watch how long it takes to produce this to produce this one. So we're looking at 45 milliseconds for the operation up top. Anyway, we'll see this in just a second, and you can see it's a lengthy operation. On your own time afterward, you can go back and recompute the derivative of sine x. I ran out of time. I didn't do a good job of gauging my time. But there is, the idea would be to go back and redo the derivative of sine x. You've got the solution, it's right down here, but go back and redo that one that we did before with the for loop, and what you'll see is something like a 60 times speed up, 60 to 100 times speed up in doing it in the NumPy way. On this one, with the nested for loops, we went from 45 milliseconds to 6 full seconds. So I call that, what is that? That's a little over 100 times. Is that right? Yeah, it's about 100 times speed up, or 100 times slow down versus the nested for loops. And this is all based on learning how to do slicing and kind of combining the operations in that way. So I'm going to leave it as homework for you to go back and compute the derivative of the sine of x. Unfortunately, our time is at an end, and I have to call it here. I'm happy to stick around and talk or whatever. And I also have a handful, I don't have enough for everybody, but I do have a handful of fantastic Diller digital t-shirts if you would like to have one. Thank you so much for your time and for your attention and for coming and for hanging out with me today. Appreciate it. I will be loading this back up onto the GitHub site so you can get my copy of the notebook that we did today. Thank you.